Welcome everyone. In order to study complex signals, we will study complex numbers in a very brief manner. So when we try to represent a complex number, we have two forms of representation, Cartesian form and the polar form. In the Cartesian or the rectangular form, we represent the complex number as z equals x plus jy, where j is equal to the square root of -1. And we refer to x as the real part and y as the imaginary part. We also write x as x equals to real part of z and y equals to imaginary part of z. In polar form, we represent z as r e to the power of j theta, where r, which is greater than 0, is the magnitude of z and theta is the angle or the phase of z. So therefore we write r as magnitude of z and theta as the angle of z. Okay. Now when we want to get the relationship between the two representations, we can use the Euler's relationship, which is e to the power of j theta is equal to cos theta plus j sine theta. So we must remember this Euler's relationship. We can plot z in the complex plane. So this is the real axis and this is the imaginary axis. So on the real axis we mark x and on the imaginary axis we mark y. And there you go, we have z. So its magnitude is r and you can see its angle is theta. So therefore we have these relationships. X is equal to r cos theta and y is equal to r sin theta, and r itself is equal to x squared plus y squared, and theta can be found as a tan 2 y comma x. I think you know why we use a tan 2 rather than tan inverse, because the angle has to be found depending on the quadrant in which the complex number is, whether the complex number is in this quadrant, this quadrant, this quadrant, or this quadrant of the complex plane. Alright, so let's take an example and see how these complex numbers are represented in the complex plane based on their angle in particular. So now consider a complex number is a node with polar coordinates r naught and theta naught and Cartesian coordinates x naught, y naught. We need to determine expressions for the Cartesian coordinates of the following complex numbers in terms of x naught and y naught, and we need to plot them. z0, z1, z2, z3 and z4 and z5 in the complex plane when r naught is equal to 2 and theta naught is equal to pi by 4. That's the first case, and as a second case r naught equals to 2 and theta naught is equal to pi by 2. Okay, so first let's look at z naught. In polar notation we write it as r naught e to the power of j theta naught, and we can write in Cartesian form as r naught cos theta naught and j sine theta naught, because you know that e to the power of j theta using Euler's relationship is cos theta plus j sine theta. Okay, so therefore we know what x naught is and we know what y naught is in terms of r naught and theta naught. Okay, now let's take the first example. z1 equals r naught e to the power of minus j theta naught. So let's consider that minus j theta naught. We use Euler's relationship once again. Cos minus theta naught is cos theta naught. Sine minus theta naught is minus sine theta naught. So which is minus y naught. So there you go. We have z1. Let's plot it later. Then when you consider z2, it is r naught. So r naught is actually x naught squared plus y naught squared. So therefore you can see that subscribes a circle in the complex plane. Z3 is R naught e to the power of j theta naught plus pi. So we write this as R naught cos theta naught plus pi sine is plus theta naught plus pi. So there you go. You have this system, and so you have minus x naught minus jy naught. Actually, this is minus z naught. Okay. Then we have item number 4. Z4 equals R naught j minus theta naught plus pi. Using the same reasoning, you can write that as minus x naught plus jy naught. And then finally Z5. Now it's just 2 pi change in the angle. So you know cos theta naught plus 2 pi sine theta naught plus 2 pi are equal to cos theta and sine theta respectively, theta naught respectively. So you have Z5 equals Z naught. So we have found all these complex numbers in terms of Z naught, and now you can plot them. So Z1 is R naught minus j theta naught. So you can Z naught is marked here because our R naught is equal to 2 and theta naught is equal to pi. Yeah, I have written them there, pi by 4. So therefore cos theta is 1 over square root of 2, and because of this 2 you get 2 times 1 over square root of 2 minus j 1 over square root of 2 for Z1. So therefore you see this is Z1. And Z2 we found to be R naught, so that's a circle. So Z naught can be anywhere on this circle. Then Z3 R naught theta naught e to the power of j theta naught plus pi. So you can see Z3 is here. Then Z4. Then finally Z5, which is the same as Z naught. Okay. Now in the next case, we have R equals 2 and theta equals pi by 2. So similarly, we can mark these complex numbers. Z2 is unchanged, but Z naught is right here, and Z1 is actually right here, and so on. The other numbers you can think on your own and see why these answers are so. Okay. So now let's take one more example. Express each of the following complex numbers in polar form and plot them in the complex plane, indicating the magnitude and the angle of each number. Okay, so let's take the first one, 1 plus j square root of 3. This is the real part. This is the imaginary part. So to get R naught, we have to square them and get the square root, and we divide each of them by that number so that we have numbers less than 1, which can be represented as angles, cosine of an angle and the sine of an angle. Okay, so that's this, and you can see the representation. Then you can get magnitude is equal to actually 2 here, and angle can be found as square root of 3 comma 1, which turns out to be pi by 3. So 2 e to the power of j pi by 3. So you can see its magnitude is 2, angle is pi by 3. So I have written the complex number over there. Minus 5 is easy. So you can write minus 5 as 5 times minus 1 plus j naught. And then you can see this is the polar representation. So you get 5 e to the power of j pi. So you can think like that and mark, or just write negative 5 over here. Okay, then this one minus 5j. So in this case you can see -1 and -1 are the components. When you compute the angle using a tan 2, you don't get pi by 4, remember, you get minus 3 pi by 4. So its magnitude is 5 square root of 2. So here is the complex number right here, and this is the angle, minus 3 pi by 4. Okay, then next one is 3 plus 4j. So 3 plus 4j, so you 3 square plus 4 squared square root is equal to 5. So you divide this by 5 and multiply by 5. So the angle is, the magnitude is 5, the angle is 8 and 2, 4 by 4 comma 3. So this is wrong, so you get 5 e to the power of j 53.1 divided by 180 times pi. That's the angle. So this is the angle in degrees, so the magnitude is 5, and here is the complex number. And then when you consider this one, 1 minus j square root of 3 to the power of 3, so you write this in polar notation. The magnitude is 2, 1 squared plus square root of 3 squared square root is 2, and the angle can be found as minus j pi by 3, 8 and 2 minus square root of 3 comma 1. So therefore you have this polar representation of the complex number which is inside the to the power of 3, and then when you raise to the power of 3, you have actually 2 to the power of 3 e to the power of minus j pi by 3 times 3, and you get this. So you can see we have marked it over there, and this angle is minus pi. So this is very convenient when you do it in polar form. So they take this as a homework and do it by yourselves. Okay, so then we need to obtain formulas for cos theta and sin theta. So you can use Euler's relationship to obtain these formulae. We can do that by starting with the Euler's relationship. E to the power of j theta is equal to cos theta plus j sin theta, and we also write e to the power of minus j theta, which is equal to cos theta minus j sin theta, because cos minus theta is cos theta, sin minus theta is minus sin theta. So now you have two equations, 1 and 2. By adding you get cos theta, by subtracting you get sin theta. So by adding you get e to the power of j theta plus e to the power of minus j theta, which is equal to 2 cos theta. So cos theta is this formula, which is something that we must remember. Alright, by subtracting we get e to the power of minus j theta minus e to the power of minus j theta, which is equal to 2j sin theta. So therefore sin theta is equal to 1 over 2j e to the power of j theta minus e to the power of minus j theta. So these two formulae are important ones for us to remember. Okay, then the complex conjugate. So if let z denote the complex variable, that is z equals x plus jy, and in polar notation r e to the power of j theta, the complex conjugate is z star or asterisk. This is the asterisk symbol. X minus jy, and in polar notation r e to the power of minus j theta. So you know that if you have 3 plus j4, the complex conjugate of that is 3 minus j4. So you just negate the imaginary part when you want to get the complex conjugate. So with this you can prove different kinds of relationships. Now let's prove this. We said z star equals r squared. It's very easy to prove. So z star, that means r e to the power of j theta times r e to the power of minus j theta. So you get r squared, and you add the powers of e to the power terms, and you get e to the power of 0, which is r squared. Z plus z star, x plus jy, x minus jy, and these cancel off, and you get 2x, which is twice the real part of z. And similarly z minus z star, you get 2j times imaginary part of z. Okay, We can go on to list some of the special values of e to the power of j theta terms. It's instructive to remember these things. So e to the power of j theta, using the Euler's relationship, we can write as cos 0 plus j sine 0. So it is 1. So always use the Euler's relationship. Excuse me. E to the power of j theta is equal to cos theta plus j sine theta. So by looking at this, you can get these values, but it's good to remember these things. So when theta is equal to pi by 2, you know that cosine is 0 and sine is 1. So therefore you get j. If your angle is angle theta is pi, cos pi is minus 1, sine pi is 0, 3 pi by 2 minus j, 2 pi 1. Okay. So let's remember these relationships values also, which would make our life much easier. So with this knowledge, we can start studying complex signals. These signals not only have a real part, but they also have a complex part. Thank you.